Any questions before we get started? I'm thinking about the take-home exam that I will give you soon next week. So I'm thinking about some problems. One of the problems I was thinking about is having you prove optical theorem. I think a lot of you do not know what optical theorem is. What? Do you know optical theorem?
Sometimes.
Okay. So I'd like you to prove it, and I think it's a good exercise. And it's a problem. H1 is on.
Oh, too weak. Too much engineering.
Okay. So if you want to learn something, you can suggest take-home exam problem for me, and then give them to you so that you can learn something. I think all of you should learn optical theorem, and in the process of proving it, you'll learn what it is. Okay. A lot of you are very naive about it. So let me know if you have anything that you'd like to learn, and if you work on in the take-home exam. So I like to keep talking about photonic crystals and periodic structures. And then you have this locate theorem. Locate wave. Okay. And one issue that often comes up is, are you coming in? No? Okay. Is of course the density of states. And this concept is often used in solid state physics. And it would be nice for us in the electromagnetic community to learn what this is as well. And I think for a very simple example of what the density of states is, we can take a box, a cavity box. It makes this box into a cavity. And then if you look at all the modes of the system, all the modes will be discretized. There's one way to make the modes discretized, but there are other ways to make the modes discretized as well. One is to use a periodic boundary condition. So another way to discretize the mode, like if you use metallic PEC or PMC boundary conditions, all the modes will be discretized. Another way to discretize the mode is to use the fact that if I have x is equal to a is equal to e to the I kx, x is equal to 0, if I have this kind of boundary condition, which is periodic, and this is only possible when x is 2L pi over a, for instance. So kx becomes countable instead of uncountable. It's not a continuum anymore. Of course, if you make a very, very large, in this 1D problem, this is just a 1D example, then this kx cannot be counted anymore. Okay, it becomes a continuum. Okay. Similarly, you can use periodic boundary condition, and you will discretize ky to be 2m pi over b, and you will discretize kz to be 2p pi over d, for instance. Assuming that this box is of size a, b, and d, for instance. If I were to draw it, it will look something like this. And then you will have b, and then you will have a, and then you will have b, or size b. Okay, this is the origin, and this will be my x. x, and this will be my y, this will be my z. So you can use periodic boundary conditions. Then, instead of allowing a plane wave solution of this kind in the box where k is arbitrary and uncountable, then your vector k has to be something of this form. 2m pi over b, and then z of 2l pi over b. And they're countable but infinite in number. There'll be infinitely many solutions to this problem, but at least you can count them. Okay, that's the cleverness of physicists. They always like to use periodic boundary conditions to make things countable, so that you don't have to do integration. You just count things. Then, if you were to look at the modes of this system, say in 2 dimensions, in Fourier space, you will find that the modes are discretized. There's a mode that exists at the origin. There will be modes that exist in discrete points in the Fourier space because of this discretization and the use of periodic boundary conditions. And they will be spaced somewhat differently in the y direction. And then in the complex xy plane, they will be spaced as such. Okay, so they'll be spaced all over the kx and ky plane. And then the size, the occupational area of each mode can be estimated because we know this spacing. We know the mode spacing in the x direction. The mode spacing in the x direction is 2 pi over a. The mode spacing in the y direction is 2 pi over b. So each of this area will be 4 pi squared over ab. Okay, so each mode takes up a space of 4 pi squared over ab. You can generalize this concept to 3 dimensions. The 3-dimensional picture is harder to draw, x, y, z. And then if you look at these modes in the 3D space, they will occupy points in the Fourier space. Let me call this kz, ky, and kx instead. They will occupy points in the Fourier space according to these rules. Okay, this discretization rules. And then you can figure out the mode volume that each mode will occupy. Each of this small volume is 2 pi over a times 2 pi over b times 2 pi over d. So each of the mode volume is actually 8 pi cubed over ABD. And ABD can be thought of as the volume of this box that I imposed the periodic boundary condition. And hence this mode volume that each mode occupies can be thought of as that. Okay? Then that allows me to count modes very easily. So if I ask myself, if I was to solve this problem, this cavity resonance problem or this periodic boundary condition problem within a frequency range, how many modes do I have? Say if I were to solve it between this frequency range, omega naught to omega naught plus delta omega. And in this frequency range, k naught is omega naught over c, where c is the velocity of light. And if I were to draw in 2D, okay, that frequency range will correspond to a shell. A shell of radius k naught in this k space, plus another one circle, and the other circle will be of radius k naught plus delta k. Okay. Then I ask myself, how many modes will I get when I look at the number of possible modes in that shell over there? The same thing can be asked in 3D. I can look at 2 different frequencies, solve this problem. This problem is actually an eigenvalue problem. It has no frequencies associated with it, but I can look for the resonant modes within a certain frequency range. I can also draw 2 spheres. Okay, 2 spheres of different sizes. And then the shell volume will be 2 pi k naught squared over 2 pi k naught square. This will be the volume of the shell times delta V, delta k naught. Okay, times delta k naught. That will be the volume of the shell that I'm drawing in 3D. In 2D, it would be 2 pi k delta k, or k naught delta k. This is in 2D, right? This is the volume of the area of the shell. And then how many modes would there be in 3D? In 3D would be equal to 4 pi k naught delta k naught divided by the volume that each mode will occupy, which is in this case 8 pi cubed over V. Okay, so the number of modes is given by that in 3D in the shell. Okay, then in 2D it would be this thing, delta k naught divided by the mode area. The mode area in 2D is given by this number over here, 4 pi squared A. Okay, so these are the two ways you can count the states. So you can use this kind of concept to easily figure out how many states there should be within a unit delta k, or delta frequency range. Of course, you can, in the limit, let A, B, D becomes very, very large, then those discretization volume will become smaller and smaller, and V will become larger and larger, and so on. Okay, so this is one way to count the density of states. But it would be nice to come up with an expression for the density of states as a function of energy, where energy is related to the operating frequency by this thing over here. In quantum mechanics, energy is obviously related to the photon operating frequency by h bar omega naught. And if you were to write this density of states function, which has the property that if I were to integrate this within a certain energy level, or between E and E plus delta E, it will give me the number of states. Okay, for all the states with energy between this thing. Delta E. Okay. Are there such a thing that I can define so that when I integrate this quantity, so this quantity would give me the number of states that I can find within this interval. So this density of states has a concept of number of states per unit energy interval. Okay. How do I write it down? It seems that there's a very clever way to write it down. One way to write it down is to just write it down like this, and then if I don't count degeneracy, I would just write the density of states in this manner. Okay. And the way why this works is because this E sub k will have many, many possible values. Like in 2 dimensions, my k vector can point in any directions. Okay, in any directions. And of course, when you pick the E sub k is a corresponding energy value that corresponds to that k vector. So I would write E sub k is h bar omega sub k, the resonance frequency of that particular mode, which is h bar k c. Okay, h bar k c, since k is omega over c. Okay. So for each of this mode, it will have a corresponding resonance frequency, and that resonance frequency has a corresponding energy value. I express this distance in terms of E sub k instead of the k vector that I show in this diagram over here. E sub k is actually related to the k vector in this manner. But for every k value that I pick, there could be many degeneracies. But if I write my formula in this way, it automatically picks it up. Okay? So this k here includes degenerate eigenvalues from that picture over there. So if you just draw a spherical shell, there could be many, many modes that share the same E sub k, but I will count them 2 times, 3 times, 4 times, or n times, depending on the number of degeneracies. But this formula encapsulates everything. Okay? So when you integrate, there's formula between a certain shell. What I'm doing is actually changing my E value. Changing my E value is like changing my operating frequency. And when I integrate, I automatically pick up using the shifting properties of the delta function, all the modes that is in that shell. So it has the same effect of doing this kind of thing, but automatic. Okay, yes?
How many degenerate modes do you get per shell?
It depends on which
for 2D,
modes.
for 2D case, in this picture.
It depends on where you are. Okay? If you are down here, for instance, you are very close to the origin. If you pick a shell that is of this radius, you only have 4 degenerate modes, right? 1, 2, 3, 4. If you pick a larger shell, you have more. Even larger shell, you have more. So for every k, so this k vector is actually different from this k vector. They're actually corresponding to different k vectors. So when I say sum over k, I mean sum over all possible k vectors that this periodic boundary condition can generate. So I can see that these 4 modes are degenerate. But in addition to this degeneracy in electromagnetics, you have the TE and the TM polarizations. Those 2 modes are also degenerate. So each k vector at this point itself can have additional 2 more. But let me just count them in there. And then just write the density of states in this manner. So when I integrate that function over a shell, I automatically pick up all the modes. And it will automatically pick up the number of modes where this Ek is in this interval, using the shifting property of the delta function. So this is a very clever way to write the density of states for countably infinite states using periodic boundary condition. Are there any questions so far? Okay, if not, then I'd like to see a, yes, yes, yes. Yeah.
Dividing by A and N3D multiplying by B.
What is that?
And N3D we're multiplying the, or is the B on the denominator or in the numerator?
Should be in the numerator, right? Because this is the size of delta V k in the k space. This is the size of the mode volume occupied by each mode in the k space. The larger V is the smaller that
So
mode
then
volume.
Y and 2D, the area is in the denominator.
Okay, I'm sorry then. Then it should be AB, yeah. It should be 4 pi squared over 8. I'm sorry. Yeah. Thank you for pointing that out. Should be up there. Okay. Thank you. Yes.
Also, Mike was asking about degeneracy. So in EM, we're not looking at the energy of the photon itself.
Right.
Or just the because photons, because usually when they do the density states, it's either like a fermionic distribution or bosonic distribution.
Right. Right. Photons are regarded as bosons. So, but each photon will have 2 polarizations, horizontal or vertical, left hand or right hand, depending on how you compose it. So each k vector actually would have 2 more degeneracies associated with it. But this, as you can see from this, are degenerate with respect to each other. But it doesn't matter. We count them all in here. You just do your counting properly. Then this is a very elegant way to write down the density of states. Yes?
Will the origin represent any state?
Origin is, in this case, the 0 state, right?
Yeah.
It's a constant. It's a constant, and most of the time we cannot excite it unless you put a constant source everywhere. Okay, or maybe you can say you can excite it if you put a source that has a non-zero DC value.
So when we count the shell, the modes in the shell, we don't count the origin.
You can count it. You can count it. You can count it, but it's not important. It's only 1 point. Okay, we are more interested in how to count the number of states per energy interval. Okay, so you can include the origin. And in fact, the origin states actually poses a big problem for the electromagnetic case. I'm just trying to work this out, but let me see if I can work this out carefully. But one of the most wonderful things is that this density of states is related to the dyadic Green's function. Okay. It's related to the dyadic Green's function. I'll explain to you why. Okay. Since we're studying dyadic Green's function, we're studying solid state physics, photonic crystals, we must well learn how to relate this density of states to the dyadic Green's function of the system. Okay. There's another concept called the local density of states, and that is given by augmenting this equation, okay, with this thing, delta E minus epsilon k n. I'm using n to denote the fact that there are actually three kinds of modes possible in electromagnetic case. You can have the transverse modes, the n modes which are also transverse but vertically polarized. And then you have the longitudinal modes. Okay. Those modes are all degenerate sometimes, and then I just use this n to denote. But I can write down this as a local density of states, which has the property that it tries to give each state a spatial distribution. Okay. This density of states here, which is called DOS, does not associate spatial distribution of the photons that are in the system, but local density of states does, which means that if you're at a certain energy level, the photon is most likely found in places where this number is large. Okay? The photons are less likely to be found if this number is small. But then if you were to integrate the local density of states over the volume, where this is defined, we're defining this over a periodic volume now, this will just give me back E minus EKN, which is equal to DOS. So if you integrate this over space, you remove its spatial dependence, because this always integrates to 1. We can normalize this mode that we have found such that this always integrates to 1. Okay. So the local density of states is often used in photonic crystals. Okay, photonic crystals, because those modes that you find will be spatially dependent. And this gives you the concept that in certain places you're most likely to find a photon. In other places you're not likely to find a photon. Say if you use photonic crystal for surface enhanced Raman scattering, you like to put your molecules at places where you're most likely to find a photon than places that you can't find a photon. So this concept is useful. Okay, you design your photonic crystals, you design the location as to where you should put your molecules so that you get the maximum excitations of the molecules or atoms by a photon in the photonic crystal. So let's
figure out Fn.
Yes?
How do you figure out Fn?
Oh, let's tell you how to find Fn. Okay. So let's do the homogeneous medium case. Let's revisit this problem. And as I said, this problem is somewhat intimately related to the dyadic Green's function of the system. So let me write down the dyadic Green's function to be the solution to this equation. Okay, where this is actually the operating frequency that we're interested in. We are actually solving this problem, which is a point source excitation problem at k naught equal to omega naught over c. So omega naught is our operating frequency. In order to solve this problem, as we have learned before, we use eigenmode expansion method, or eigenfunction expansion method. We find eigenfunctions that satisfies this equation. Okay, we found eigenfunctions and use this as the eigenfunctions to expand this dyadic Green's function G. So this is like a rehash, but let me rehash it using a different light. So we found 3 different kinds of Green's function, and as I said before, I'm going to use periodic boundary condition to make my K into a periodic one, so that it's countable, countably infinite. So my K is countably infinite. When I say sum over all K, I mean sum over all L and P here. That's what it means over here too. But it's sum over all K and sum over L, M, and P. And physicists often like to use this notation. It's a shorthand notation. Instead of writing L, M, and P very easily, we just put K. Okay, so it sums over all K. So when I look at this problem, I could have 3 kinds of solutions. If Z is pointing vertically, then I have, as we have seen before, for each K value, we can define a normalized vector wave function. Okay. It's hard to normalize this vector wave function if the volume is infinite, but for a periodic boundary condition case, in the finite volume V, you can easily prove that this is a normalized vector wave function. It has a property that when you perform this integration, it goes to 1. Okay, I hope I don't have the proof to use for that. And one of the things is that if K vector is pointing that way, okay, so this is actually pointing horizontally. So M is a vector wave function that's horizontally polarized. So you can think of it as corresponding to horizontally polarized electromagnetic field. The N function can be written as 1 over K curl of M function as we have done before. And if you work it out properly, it actually corresponds to I K hat cross M. KR. So if N is horizontally polarized, K hat is pointing in a direction, then N function is something that points in that direction. So N can be thought of as a vertically polarized mode in this periodic boundary condition. If you normalize it properly, you can easily show that the 3 factors should be IK hat instead of IK. And this is the N function that's normalized. And then we have the 3rd type, as we have found before. And these are the longitudinal ones. They're proportional to the gradient of the scalar wave function. And to normalize it, you have something that looks like that. Okay? These are the longitudinal. Wave function. These 2 are the transfers. Okay, so you have the longitudinal one as well as the transverse ones. And we have them all normalized. And we have this normalization property so that if you multiply 2 of them and integrate, if you multiply 2 of them together and integrate, you get this orthonormality property that it should be delta L, L prime, delta M, M prime, delta P, P prime, furthermore delta N, N prime. So if they belong to different polarizations, they are also orthogonal. Okay. They are also orthogonal within themselves if they belong to different modes, is what it says. If the K's are different, if this K and K prime are different, they will be orthogonal. But if N and N prime are different, which means that they belong to different modes, then they are also orthogonal. So Fn N is equal to 1 or 2 represents N and N. Okay, I'm going to use this notation. F3 represents the L modes. Okay, I'm going to use this subscript N to represent these 3 different kinds of modes that we have. 1 and 2 correspond to the transverse modes. 3 actually corresponds to the longitudinal mode. Okay, just a very shorthand notation. Then I can use the fact that they are complete and orthonormal, I can define an identity operator very easily. You can derive it yourself too, but if an identity operator, it's just the outer product of all these vector wave functions which form a complete set. Okay, this is just the thing that we have written many times over, and any kind of thing. You can think of it as the coordinate representation of that operator. Okay, coordinate representation of that operator. You can easily show that, and that this should be an R prime. Okay, any problem with that? Or you can do it by simple algebra using the orthonormality. Okay. So if I substitute my direct Green's function to be also expanded in terms of this vector wave function, it should be a diode, so it should be this vector wave function times another vector that I do not know what it should be at this point yet. I can substitute this into this equation, substitute that Green's function into this equation, substitute the representation for I onto the right-hand side. I do all the derivatives. The derivatives operating on the vector wave functions is very easy to perform because the vector wave functions are solutions to this equation. They will always produce a k squared. And then you can get the direct Green's function very easily. And should be something of this form. Okay, so this is the generalized way to write the direct Green's functions, where k1 equal to k2 equal to k, k3 equal to 0. Okay, k1 and k2 are the eigenvalues that correspond to the transverse modes. And we can easily show that this transverse mode gives eigenvalues of k squared in this equation. The longitudinal mode, when n is equal to 3, represents the longitudinal mode. And you can easily show that the longitudinal mode satisfies this equation with k equal to 0. Okay, so that's a shorthand way of writing this direct Green's function. Then let's try to give this some physical meaning. What is this expression actually saying? This expression is saying the fact that the direct Green's function of a homogeneous medium in a region bounded by periodic boundary condition can be expanded in terms of the modes of that region that we have found using periodic boundary condition. And that if the operating frequency k0 is the operating frequency, is close to any of these eigenvalues that we have found, what will happen to this expression? If you pick the operating frequency very close to any one of these eigenvalues, it will be singular, right? It will be singular. So if you do an experiment in the lab and just switch the frequency, you see a lot of peaks. You see a lot of peaks. Those peaks correspond to the coincidence of the operating frequency with the resonant frequency. But there's also a static mode. There's no resonant frequency, or the resonant frequency is 0. And as you have seen before, plenty and plenty of modes that belong to that class. So there's a huge degeneracy over there. So the origin, if I were to put this in the origin is actually a big hole, a black hole that has many modes in it. And those all belong to that. So let's not count those. Those are troublesome to count. Actually, infinitely many of them. But then, each k vector, if I find a discrete mode k vector, it will have, it might be degenerate with other k vectors that belong to the same circle. As I perform this experiment, I'm actually moving on a circle, right? When I perform this experiment by sweeping the omega and changing the radius of this circle over here, I might be hitting myself with other degenerate modes that also lie on that circle. But within this k vector itself, there are actually two degenerate modes already, m and n, the horizontal and the vertical polarized. Okay, so electromagnetic transverse modes always have two degenerators. Okay, like electrons, they always spin up and spin down, but then for electromagnetics, it's vertical, horizontal, or right hand or left hand circular with polarized. Okay, so one interesting thing that you can show is that the local density of states is actually very much related to this function over here. Okay, you already start to see peaks when you think about this experiment. If you do a conjunction experiment, you start to see peaks. Okay? But what happens to those peaks if there is a loss in the system? If there's no loss, you see a very sharp high Q peak. You see a very sharp high Q peak. Right? It looks something like this. As you sweep your omega naught, you see all these kind of peaks. But as you make the loss bigger and bigger, the Q of the peak starts to decrease, and then the thing will look something like this. If there's some loss in the system. And the more loss there is, the lower the Q, and the broader the peak would be. Okay? But so this is like the density of states, but not like the density of states, because in the